Welcome, curious minds, to another deep dive. Today, we're embarking on something pretty incredible. Humanity's spectacular, 50-year adventure exploring our solar system.
Yeah, it's quite a story.
We're going to unpack how we went from just, looking up from Earth with telescopes, maybe finding the odd meteorite,
Right, basic stuff.
to actually sending robots, robotic emissaries, across the whole system, every planet, moons, even Pluto, and crucially, what we've actually learned.
Exactly. And it's not just what we found, though that's amazing, obviously. What's really fascinating, I think, is how we pull it off. I mean, the ingenuity and who was involved, the people behind it all.
Yeah, the unsung heroes sometimes.
Totally. And the political forces, the social context, the tech challenges, all that stuff shaped this whole grand adventure. Our sources, well, they cover everything from old mission reports to budget analyses, so it's pretty comprehensive.
Okay, so let's start at the beginning. How did we make that first leap? You mentioned Mariner 2 earlier.
Yeah, Mariner 2, that was NASA's first successful shot beyond Earth, headed to Venus in 1962.
Right. And before that, it was just telescopes and meteorites, like we said. Pretty limited view, really.
Absolutely. We were basically guessing about a lot of it. Mariner 2, though, it was our first, direct taste of Venus.
So what did it carry? What instruments?
Well, it had a whole suite of things for the time. Radiometers for temperature, a sensor for tiny meteorites, detectors for solar plasma, charged particles, and a magnetometer.
And the big discovery.
Huge ones. It confirmed Venus was, well, a hellhole, like 900 degrees Fahrenheit surface temp.
Wow.
Got our first basic atmospheric readings. And crucially, it detected the solar wind, that constant stream of particles from the sun. That changed everything.
Right, our understanding of space itself.
And it confirmed Venus doesn't have a magnetic field like Earth does. Big difference.
Okay, so you sent a probe millions of miles away.
Yeah.
How do you even track it? How do you talk to it? That sounds like a nightmare.
Yeah, that was a massive hurdle. And the answer was the Deep Space Network.
The DSN, those giant dishes you see pictures of.
Exactly. A global network, constantly upgraded. It handles the tracking, the data, the navigation. But it's more than just NASA's network, right? It became this huge international effort.
So it set the standards for everyone.
Pretty much. Forging how all space agencies track and navigate deep space probes. It took time, though.
How did that standardization even begin?
Well, a lot of the groundwork came from earlier missions, actually. JPL's Ranger missions to the moon back in the early 60s.
Oh, right, the moon missions.
Yeah, they had some spectacular failures early on. Lots of learning the hard way.
I bet.
But Ranger 7, 8, and 9 were big successes, sent back thousands of really high-res moon pics. And doing that, figuring out how to command them, get the data back, that directly fed into designing Mariner 2 and building the foundations for the DSN.
Gotcha. So as we started going further, rockets alone weren't enough, right? We needed clever tricks. Which brings us to gravity assists.
Ah, yes. The cosmic slingshot. Brilliant concept.
Explain that. How does it work?
Basically, you fly a spacecraft close to a planet, and you use its gravity to, fling the spacecraft faster, or sometimes slow it down, all without using propellant.
Free speed.
Pretty much.
Sure.
Mariner 10 was an early pioneer. Used Venus to swing by Mercury 3 times back in '74.
And Messenger did something similar later, right? To orbit Mercury?
Exactly. Multiple flybys of Venus and Mercury to finally get into orbit in 2011. This trick, the gravity assist, it really unlocked the outer solar system, made missions feasible that just weren't before.
And speaking of the outer solar system, Voyager. You can't talk about this era without talking about Voyager.
Oh, absolutely iconic. Launched in '77 and just perfect timing.
Why perfect timing?
There was this rare alignment of the outer planets. Jupiter, Saturn, Uranus, Neptune. Happened only once every 175 years or so.
Whoa.
It let Voyager 1 and 2 use gravity assists from one planet to get to the next. A grand tour, they called it.
And the discoveries were just stunning.
Mind-blowing. Active volcanoes on Jupiter's moon, Io. First time ever seen off Earth. And the details in Saturn's rings. The complexity, the braids. Stuff we never imagined.
And Voyager 2 went even further, didn't it?
Yeah, that's the unique one. The only spacecraft ever to visit Uranus and Neptune. Just amazing flybys.
And they're still going?
Yep. Voyager 1 entered interstellar space, the space between stars, back in August 2012.
Wow.
Both are now in their 4th decade out there. Just incredible engineering and longevity, pushing the boundaries constantly.
So, building on Voyager's legacy, what came next for the really distant parts of the solar system?
Well, you got to talk about New Horizons, a different class of mission, the New Frontiers program.
You went to Pluto, right?
Exactly. Made the first ever reconnaissance of Pluto in 2015. A dwarf planet, but a huge milestone.
And with that, NASA had visited every major type of body.
Pretty much. First agency to complete that initial exploration of the whole system. New Horizons also used a Jupiter gravity assist, by the way.
Ah, that trick again.
And it's still going. Headed deeper into the Kuiper Belt now, that region beyond Neptune. Still sending back data.
So looking back at all these missions, there's a clear pattern, isn't there? Like steps, flybys first, then orbiters.
Right. You do a flyby, get the basic lay of the land, figure out what's interesting. That helps you justify and plan an orbiter mission.
And the orbiters give you the detailed maps.
Exactly. High-resolution data, which you absolutely need if you're going to try and land something, like a lander or a rover. You need to know where it's safe to go.
Mars is the perfect example of this, isn't it?
Oh, absolutely. We went from flybys to orbiters like Mars Odyssey and MRO, giving us incredible maps.
MRO, Mars Reconnaissance Orbiter.
Right, and those maps were essential for landing the rovers, like Spirit, Opportunity, Curiosity, Perseverance. And it's not just NASA now.
No, it's a crowd up there.
Yeah, you've got ESA's Mars Express, India's Mars Orbiter mission, NASA's MAVEN studying the atmosphere. It's this international effort, each mission building on the last, asking deeper questions.
Let's shift gears a bit. We talk about the missions, the tech, but what about the people? You mentioned the unsung heroes. Beyond the famous astronauts or engineers like von Braun or Korolev, who are the folks who actually made robotic exploration happen?
That's such a good point. And our sources actually say, we still need a proper social history of space exploration. We know the astronauts' stories, but the thousands of engineers, technicians, scientists behind the robots, less so.
And the diversity or lack thereof, like gender representation?
Yeah, the sources point that out too. For the first, say, 25, 30 years, engineering systems management, overwhelmingly male.
But that's changed a bit.
It has. The sources mentioned, like mission control for the Curiosity rover landing at JPL, a marked contrast, they called it, with many more women visible, though they also note the engineers building Curiosity. Still mostly male. So progress, but
still a way to go.
Exactly. And think bigger picture. For decades, it was mostly the U.S. and the Soviets, Russia. Then Europe, Japan, China, India joined in.
So comparing the people involved internationally, that could be interesting.
Hugely illuminating, potentially. Comparing gender, ethnicity, class backgrounds of the people building spacecraft in different countries. Plus, the internal politics mattered, like bureaucratic infighting in the Soviet program or China's model integrating civilian and military space efforts. That stuff shapes how things get done.
And the politics extends to where things get done too, right? Launch sites, tracking stations. It gets complicated.
Yeah, the sources touch on that. It's an interesting angle. They talk about colonialism here on Earth in relation to space.
How so?
Well, the Soviets launching from Kazakhstan, the French from French Guiana, those locations weren't chosen in a vacuum. They have histories.
And the DSN tracking stations.
Right. They're scattered globally.
Right.
The one in South Africa had to operate under apartheid for years. How did that affect the work, the interactions? The sources raise the question, suggesting these geopolitical realities definitely shape the logistics, the diplomacy, even if the day-to-day engineering impact isn't always clear. It reminds you, science doesn't happen in a bubble.
Absolutely. So let's get into that classic debate, robots versus humans. Besides the moon, only robots have actually landed on other planets. So what is exploration when it's robotic? Is it just numbers and pictures?
That's a really fundamental question. I mean, is exploration getting data points, taking images, bringing back samples? Each choice drives the technology you build.
Right. If you're looking for microbes, you need different instruments than if you're mapping geology.
Precisely. So how we define robotic exploration directly shapes the spacecraft design, the instruments, and ultimately what we can discover.
But, there's also got to be a bit of fun in it for the engineers. I mean, landing a car-sized rover on Mars using a sky crane, that's wild.
Totally. You read accounts, and there's this real sense of, delight in the audacity of it. Let's deliver this thing 35 million miles and drive it around.
So it's not just technical solutions, it's that spirit.
I think so, yeah. That desire to tackle the impossible, to come up with these crazy, brilliant ideas like airbags bouncing on Mars or the sky crane, that definitely fuels innovation and resilience when things inevitably go wrong.
And a huge part of making all that possible has been computers, right? Onboard computers.
Absolutely pivotal. Our sources talk about feedback loops of capability and complexity. Basically, better computers allowed more complex missions, which demanded better computers, and so on.
And that was the difference between U.S. and Soviet approach.
Yeah, a key one, yeah. U.S. designers could often update software mid-flight. Think Mariner 9 arriving at Mars during a global dust storm.
Oh, right.
They could tell it to wait, let the dust settle, then start mapping. Soviet spacecraft were often hardwired, less flexible. If they hit a storm like that, well, sometimes they didn't survive. That software flexibility was huge.
Interesting. So with all this tech advancement, why are we still launching, SUV-sized spacecraft? Why didn't miniaturization take off more for planetary science?
That's a really good question the sources raise. And the answer seems to be it's not purely technological. It's programmatic, basically, political and cultural, meaning big planetary missions are still mostly the domain of nation-states. They require huge budgets, political backing, and often there's a preference for these big flagship missions that showcase national prestige and capability rather than lots of smaller, maybe riskier missions. It shows, as one source puts it, how we do it continues to reflect who does it.
And while the spacecraft get the glory, let's not forget the people on the ground, those DSN engineers you mentioned, in the desert, listening.
Yeah, the explorers on Earth. They're absolutely vital. They're the link. They translate our commands. They catch the faint signals coming back.
They're not just button pushers.
Not at all. They're problem solvers, innovators. The sources highlight cases where DSN engineers literally saved missions with their expertise, pushing the limits of telecommunications. We wouldn't hear from Voyager or Cassini without them.
Which brings us to maybe the biggest question. Why? Why do we do all this? There's that famous story, right? The nun writing to NASA.
Sister Mary Gioconda, yeah. Writing to Ernst Stillinger in 1970, asking how he could justify spending billions on Mars when children were starving. A powerful question.
And Stillinger's reply became kind of the classic justification.
Pretty much. He laid out this whole litany. The budget isn't zero-sum, so the money wouldn't just magically go to feed kids anyway. Plus, understanding Earth by studying other planets, climate, geology, international cooperation better than war, right? Inspiring kids in science and tech.
And the spin-offs. Everyone talks about the spin-offs.
Right. Computer animation, solar panels, medical imaging, even the Super Soaker, famously developed by a JPL engineer.
Didn't know that one.
But Stillinger himself admitted relying only on spin-offs to justify the cost is a thin reed. The primary value is the exploration itself.
And the cost, when you put it in perspective, it's not actually that enormous compared to other government spending, is it?
No. Like, the Curiosity rover cost less than what the Pentagon was spending per week in Afghanistan around that time. Or the entire planetary science budget being like one Starbucks coffee per American per year.
Puts it differently.
It does. But here's the paradox. Despite that relatively low cost and the amazing discoveries, polls often show public interest in space is kind of low. Maybe only a quarter of Americans really follow it closely.
Yeah, landings like Curiosity get millions of viewers online. Viking, Pathfinder, Voyager, huge media events.
Exactly. Massive attention for the big moments. People like Carl Sagan, Neil deGrasse Tyson, they've done wonders popularizing it. But that sustained day-to-day public engagement, it's tricky.
I remember seeing the pictures of the Space Shuttle Endeavour being moved through LA in 2012. 1 million people came out just to see it crawl down the street.
Incredible outpouring, right? Pure spectacle and pride.
But then, as the source points out, when those same people voted a couple of weeks later, space policy probably isn't top of their list. Why the disconnect?
It boils down to the political economy of it all. NASA's budget, while significant, is a tiny slice of the federal pie. And how that slice gets allocated often depends on bigger national priorities, things outside NASA's control.
Like those shifts over the decades you mentioned.
Right. The moon race in the 60s boosted funding. Then the energy crisis shifted focus in the 70s, health research in the 80s, defense after 9/11. Each wave impacts NASA's budget, and planetary science often feels those ripples strongly.
Which led to things like the lost decade for planetary science in the 80s, low funding.
Exactly. Very lean times. Contrast that with the early 2000s, 2003, 2006 specifically, when planetary science actually had its highest funding levels ever. Huge difference in what could be done.
And other science areas within NASA, like Earth science or astrophysics, they have their own budget histories.
Totally different paths sometimes. Earth science, for instance, got a big boost in the early 90s, became a major priority. That means resources flow differently depending on the political climate and perceived national needs. It directly shapes the science we do.
And NASA itself was born out of these kinds of pressures, right? Post-Sputnik.
Absolutely. The International Geophysical Year laid some groundwork, establishing satellite overflight as peaceful. But Sputnik really lit the fire under the U.S. The Space Act of 1958 created NASA, and its very first goal was expansion of human knowledge of space. Science and national prestige intertwined from day one.
Then James Webb, the administrator, tried to put science on an equal footing with human spaceflight in the structure.
Structurally, yes, but in practice, human spaceflight often still got the lion's share of attention and budget.
Which didn't sit well with scientists.
Not always, no. That criticism led to advisory boards like the Lunar and Planetary Missions Board, giving scientists a more formal voice in planning, trying to ensure science goals weren't sidelined. An important step.
Okay, jumping ahead to the 90s. Faster, better, cheaper. Daniel Goldin's mantra, what was the real aim there?
Well, the official goal was to fight the trend of ever bigger, ever more expensive missions. Launch smaller, faster, cheaper probes. Get more missions flying.
Sounds good on paper.
Yeah, but the sources suggest there was also an internal push to make science cheaper, to free up money for human spaceflight ambitions. Kind of a double-edged sword.
And it led to some pretty high-profile failures.
Tragically, yes. Mars Climate Orbiter and Mars Polar Lander, both lost in 1999. Built on what they called success-oriented engineering, basically, cutting corners on testing and redundancy to save money. It backfired badly.
So FBC was scrapped.
The strict, high-risk version of it, yes. But some ideas survived, like pushing for multidisciplinary teams, being more agile. But the lesson about not sacrificing reliability for cost was learned the hard way. NASA had to recalibrate its approach to risk.
Even with those setbacks, the 2000s were good for Mars, right? A renaissance.
Definitely. Budgets increased, lots of missions launched, and the New Frontiers program started for those medium-cost missions like New Horizons to Pluto and Juno to Jupiter. Big successes.
But not everything got funded. Mars sample return, that keeps getting canceled, doesn't it?
Yeah, that's the white whale. A top scientific priority bringing Mars rocks back, but canceled or deferred multiple times, like in 91, 2000, 2011.
Why? Too expensive?
Partly, but often it's budget shifts. Money gets moved to prop up human spaceflight programs, or other big science projects like the James Webb Space Telescope need more funds. It shows how vulnerable even top priority science can be to shifting political winds.
Which really underscores that role of the NASA administrator as the person bridging science and politics.
Absolutely, they were boundary spanners. Goldin used a failure to push FBC. Michael Griffin focused on constellation, cutting science, but weirdly, his delay of the Mars rover Curiosity probably saved it.
How so?
Gave them more time to fix technical problems that might have doomed it otherwise. Then Charles Bolden pushed for more international collaboration, like with ESA on Mars. They all had different priorities, different styles, but they all navigated that science-politics interface, shaping what actually flew.
And that international collaboration you mentioned, it's become essential now, hasn't it, for the really big, expensive stuff?
Oh, it's basically a must. Take Cassini-Huygens at Saturn. A massive joint effort. NASA built Cassini. ESA built the Huygens probe that landed on Titan.
That Titan landing.
Yeah.
Amazing. ESA's first big outer solar system mission, right?
Exactly. And the Italian Space Agency provided Cassini's main antenna. You couldn't do a mission that complex without pooling resources and expertise globally.
And speaking of global partners,
Yeah.
Australia's Parkes Radio Telescope, it played a huge role from the start.
Huge. Its design actually influenced the DSN's big antennas, and Parkes has been involved in so many key moments.
Like what?
Tracking Mariner 2 way back when, supporting Apollo, linking up with the DSN for the Voyager encounters at Uranus and Neptune. But the most dramatic, probably Huygens.
The Titan landing again? What happened?
There was a sequence error on the Cassini orbiter. It wasn't going to record all the data from Huygens as it descended through Titan's atmosphere. Potential disaster. But Parkes, along with Green Bank in the U.S., they were basically listening in. And their recordings captured the missing data. They literally salvaged the entire experiment, as the source says. Incredible save, all thanks to that international network being there.
Wow. That's a fantastic story. So collaboration isn't just about cost sharing. It can actually save the science.
Absolutely. And you see this transnational flow of ideas and tech in other missions too, like the Ulysses Solar mission with ESA. It wasn't always smooth, but it worked.
Okay, let's touch on a weird historical footnote. The bacteria on the moon story.
Ah, the Streptococcus mitis controversy. Yeah, after Apollo 12 brought back parts of the Surveyor 3 lander, some scientists claimed they found these Earth bacteria still alive on it, having survived years on the moon.
Seriously?
That was the claim. It kicked off a huge debate about planetary protection, not contaminating other worlds and not bringing alien bugs back here.
And was it true? Did they really survive?
Well, NASA's planetary protection officer at the time, John Rummel, strongly challenged it, argued it was much more likely lab contamination after the parts got back to Earth. But the source says the issue will never be resolved for sure.
Which raises huge questions for sending humans to Mars, right? Can we even avoid contaminating Mars if we send people?
That's the multi-billion-dollar question, isn't
Mhm.
it? A massive challenge for future exploration.
Shifting gears one last time. Pop culture. Space is huge in movies, books, asteroid impacts especially.
Oh, yeah. A classic trope since, like, the 19th century. But it really hit a peak in the 90s, right? Armageddon, deep impact.
Probably helped by that comet Shoemaker-Levy 9 actually hitting Jupiter. Made it seem real.
Definitely focused minds. But here's the funny thing. Despite Hollywood loving killer asteroids, the public, not that worried.
Really? Why the gap?
Well, researchers like Paul Slovic have frameworks for risk perception. Asteroid impacts are weird. Super low probability, but super high consequence if it happens.
The ultimate disaster movie scenario.
Exactly. It hits those dread risk and unknown risk buttons hard. Makes for great drama, even if people don't list it as their top everyday concern.
But scientists are concerned, right? NASA's planetary defense budget has gone way up.
Oh, yeah. From a few million a year to like $150 million by 2019 for near-Earth observations and defense planning. It's taken very seriously.
So does Hollywood help or hurt getting public support for that? The drama versus the real science.
Good question. Maybe raises general awareness. But does it educate accurately? Probably not always. It connects to how science gets communicated overall.
How has that changed?
Think back to Voyager. Journalists covered it, often adding emotion, humanizing the scientists to make it relatable.
Yeah.
Print, TV dominated. Now, think Cassini. The mission had its own website releasing images and info directly. Online news, social media. It's much more immediate, less filtered sometimes, but maybe also harder to capture that shared sense of wonder.
And the cultural mood has shifted too, hasn't it? Talk of a war on science, more cynicism, Hollywood doing space battles instead of hopeful futures.
Yeah, the sources note that shift. Is space exploration losing some of that romantic shine as it becomes more familiar? Will the novelty wearing off lead to less public enthusiasm? It's a real concern.
So, as we wrap up this deep dive, it's clear this 50-year journey has been an incredible human story. A third age of exploration, as one source called it.
Definitely. And it forces us to think about the value, you know? Niels Bohr said science is about the gradual removal of prejudices. Maybe space exploration, by showing us other worlds, helps us remove our Earth-centric, human-centric biases, like Copernicus or Darwin did in their time.
So, for you listening, what's the takeaway? Does exploring space enrich us? Is it a cultural need? Does it give us critical knowledge, economic benefits, better international relations? Does it improve education, quality of life? Maybe even feed some spiritual need?
And looking forward, in a world with limited resources and so many competing priorities, how do we make sure space exploration keeps benefiting humanity? How do we ensure this collaborative journey into the unknown continues, inspiring the next generation to keep looking up? That's the challenge for the next 50 years.